listening on the direction for pedestrian calls and
There are like a couple of equations along the way, but we'll remind you of them. Okay, so we'd like to talk about exponential applications today if that's not already been made clear. And I've given you a gift in front of you. You have a handout because I'd like not to have like half of your time be spent writing down, suppose you triple your number, right? Let's just do math, right? I don't want to be like writing a whole bunch of word problems. So there they are in front of you. And for the most part, that's what we're going to be driving this lesson by using these examples. We do have a couple of little equations to start notationally remember some of the things you might have learned from Algebra 2 a little bit. And the other thing we need is some readers. Okay, so who's going to read the first one, for example? Rosie is so excited. Go ahead. Don't worry, I'll get you guys.
Suppose you triple your number of Instagram followers every 5 days, and you have 200 followers right now. Assuming this behavior continues, write a function f of t that gives the number of followers you have after t days. Also, compute f of 10 and interpret its meaning.
Wonderfully read. Okay, yeah, Isabel. You don't have to write what? Right. Yeah, right. Good. Yeah, I'm kind of telling you what I want the variables to mean. Okay, so just to make things less challenging, for at least the time being, let's ignore the every 5 days thing and just pretend that it's tripling every day. Okay, and then we do want to answer the question as it was asked. I promise, and we will. But let's just make it simpler for the time being and answer this question. And suppose that we have 200. We start with 200 followers, and we triple, let's say daily. Just let's say that. How would you compute that? So on the 0th day, you have 200 followers. On the t equals 1, after the first day, you have how many followers? 600 because you triple every day, we're going to say, just for now. At the end of 2 days, when t is 2, you have 1,800 followers. Are you feeling this? Okay. All right, so how would you model that? Not this, but that. It triples every day. Every day. Yeah, Eric, go. 200, say it again. Times 3 to the t. All right. So does that do what we just said it should do? Like if you plug in 0, do you get 200? If you plug in 1, do you get 600? If you plug in 2, do you get 1,800? I think so. And so I think that, and the reason I start with that, I think, is because like that's a model that you're comfortable with. Start with 200 and triple. Cool. But that is actually not what the problem says. It says every 5 days. So let's now actually introduce that requirement back in here as well. So how can we adjust our model? Now it's all of a sudden wrong. What do you think? Taylor, you want to take it? The whole thing, like, what do you mean? The whole thing? Like the whole board? The whole Promethean board? 3 to the t over 5, so am I putting over 5 here?
Both the 200.
Like that?
Yeah.
All right, so I claim then, right, at t equals 0, we should still have 200 followers, right? If t is 0, we should still get 200, and that doesn't, there's something, I love how you're thinking though. But it doesn't seem like that's working. If I plug in t equals 0 into your formula, I still need to get 200. I don't. You feeling me? Okay. No, I'll take it. Put the t over 5? Okay, I'm going to put your model to the test too. Let's see. Let's make sure this works. If you put in 0, do you get 200 still? Okay, I like that. If you put in 5, it should be true that we've tripled. Do you get 600 when you put 5 in? Ooh, okay. So I think I kind of like this, and it kind of feels right too. Doesn't it feel right to you as well? By the way, what kind of transformation did we just apply to this graph? If we cover up the divided by 5, and then we introduce the divided by 5, what transformation of the graph has been applied? It's a horizontal something? It's a horizontal stretch by a factor of 5. And that should reckon well with what we meant to do in the problem too. Didn't we mean to take it from a daily model and stretch it horizontally out to a 5-day model? So, all right, this is all working with all of our intuitions, and mathematically it seems to be working out. So I think we can call it a day. And f of 10, actually we already we actually already computed this verbally. What did we say F(10) is? 1800, right? Let me stop and ask you some questions though too about interpret its meaning, because that's 1800 followers, right? So I should say 1800 followers, whatever you want to write there. 1800 followers. Does this represent your Instagram account pretty well? Okay. I know it does not. It's just, that's exactly what the phenomenon is occurring to my Instagram.
At what day do you reach the maximum number of Instagram users?
That's a good question. Yeah, now that there are like a billion Instagram users, or something, or no, whatever it is, 100 million. What are they at? It's big. It's a lot.
Well, the question of users.
That's true. That's true. All right, wait. I have some deep follow-up questions. Okay, are you ready? Are you ready to go deep?
Yes.
Are we allowed to ask? I know the answer. 5 days from any time right now, I will have triple the number that I have right now. I get that. What about tomorrow though? Like if I have a certain number of Instagram followers today, how many more? What's the growth factor over 1 day? Isn't that a valid question to ask? Like how much do I expect tomorrow to have? Like does it make sense? Another question that could kind of go along with this is, does it make sense to plug 1 into this model? Like of course it should, right? It should. And what are you multiplying by each day? I don't know. Judah?
Technically, the implementing function that really completely ends it, because all that we need is to triple the Instagram followers every 5 days, and just to start with 50 followers. Right?
Yeah, let's assume that like there's some we should have said that maybe at the beginning, that we assume exponential behavior. In which case, then this is the only model. But you're right. Yeah, we could have had some kind of disjoint thing happening in between. Or you could jump up at a certain Rosie.
Like directions you give us, and like we have no way to know how much it grows every day. Like it could, like you could have
like I said, let's assume
followers in the first like
that's, both of you have
4
raised.
days,
You're right. You're right. So we've just assumed. You and Judah are raising the good issue. You're right. I didn't say that, but let's assume on the face that this kind of exponential behavior is what's always happening in between. Each exponential data point, we have something exponential happening also. Let's just make that assumption. Even though you're right to say that is an assumption. So yeah, it could be going like crazy in between. You're right. That being said, what do we multiply by then each day? We can make this more obvious by rewriting this just in a simple way. What is it? 200? 200 times 3 to the 1/5 all to the t. Okay, that's another way to rewrite that. Does that make it clearer? What are you multiplying by each day? I mean, the thing you multiply by each day, it should be true if you do that, if you multiply by something, and then you multiply by that same thing again, and then again, and then again, and again 5 times. It's you actually just having multiplied by 3. So what number can you multiply by itself 5 times to get 3? How about we just call it the 5th root of 3, right? So that's our daily growth factor, isn't it? Every day you multiply by the 5th root of 3 to get to the next day's amount of followers. And by the end of 5 days, what have you done? You've tripled it, haven't you? Have you thought this through before? I don't know. I think it's useful to think this through. It's a powerful idea. It actually makes me think of music. Okay, that's what it makes me think of. Sorry, this is where my mind goes. So do you know what you multiply by the frequency of like an A to get to the next highest octave A? What do you multiply the frequency by? It is called 1 octave, but you actually multiply by 2. Yeah. So if you have an even tempered 12 scale, 12 half steps from A to A, the next higher A, then what do you multiply by to get to the very next half step up from an A? Root what? Something. Yeah, the 12th root of 2, right? Because if you multiply by the 12th root of 2, you get to a nice new value. And if you do that 12 times, you multiplying just by 2, which is an octave. Yeah. So anyway, that's something that makes, I think of the 12th root of 2 anytime I think of like an even tempered scale. Right, if you think of music. All right. So it's the same kind of thing. You know, over a course of time, are you multiplying by 2? Okay. Well then. Or we could ask another cool question here too. What's your growth factor per minute? Right? Can we figure that out? Or per hour? Per hour it'd be the 120th root of 3 per hour, right? Over 24-hour period, 5 24-hour periods. Anyway, are we having fun yet? Okay. Sorry. I apologize publicly to Miss McDonald. That's her old name. Okay. Fix that on your sheet, please. Okay. Where's my next reader? I know that we had some excited readers out there who are ready to read. So, Isabel, go ahead next. We're going to see you next. Simmer down.
First city has a population of 10,000 at 1 p.m. when she starts playing. In how many hours will the population reach 25,000?
Brilliant.
Can we use our calculators on these?
Of course we're going to use our calculator on these, yeah.
Okay, I was just making
So,
sure.
all right. What do we do? Defining variables. Okay, what would you like? Let's let T be, or H, or what do you want to do for the number?
S for sin.
No, well, okay. For the population of SimCity, you want to have S? Okay.
No, wait, no, it'll look like a 5.
Oh no, no.
It'll look like, how about we let P be a P of, what are we going to call, what's the independent variable? H, you like H? Be the population after H hours. Is that okay? After H hours after 1 p.m., I guess we could say. Okay. So can you give me a model? P of H is equal to 10,000 times something to the T. Okay. Maybe. Or excuse me, H. I guess we're using H. All right, so this is a little bit of a tricky thing to think about what the growth factor is each time, right? We need to think about what are we multiplying by? Well, every time as we move from 1 hour to the next, we want to multiply by something that increases the value by 2%. So what do you multiply by to increase the value of something by 2%? 1.02, right? If you were like working at a store and you wanted to go through and mark up all of your prices by 2%, you would go through and multiply all of your prices by 1.02. And you would have marked up everything in your store by 2%. That's what you would do. Or if you wanted to give a 2% tip because you're really stingy and mean, you'd multiply your bill by 1.02 and you'd get your total bill cost, right? All right, so that discussion I think you've had maybe before, but it's good to have again. That was the hard part of this. Equals, we want this to equal 25,000. So go for it. What do we have? 1.02 to the H equals 2.5 once we divide by 10,000, so that H equals log base 1.02 of 2.5, which is approximately something.
46.271169.
46 point, say it one more time,
271169.
Is there 2 2's in there?
No, 2711.
All right, that's good enough. 1 1. All right. And there's more, right? But let's round. This is in hours, right? Let's round to the 10th place, and I'll tell you why in a second. You're not gonna like it. It says in how many hours? So I think we answered the question. It didn't say at what time or anything. But it's approximately 2 days later. She's like done nothing but this all of the last like almost 2 days. With occasional bathroom breaks, maybe. Okay. She didn't sleep. All she did is play SimCity.
Nice.
Yeah, yeah. Now, the reason I rounded to 10th place, you're not going to like this, the last class when I mentioned this word, they all groaned. It's because we're going to start practicing. We're going to start practicing something. I don't think we've had to round at all this year, amazingly, so far. IB would like you to round to 3 significant figures. Good, you're right on cue. Thank you. Okay. So that means for this particular case, we don't mean 3 decimal places. We mean 3 significant figures. So, and this is yeah, you have a 0 in 1 place. All right. So listen. I know that's very exciting, I can tell. So we will have a continuing conversation about what that means for us, but I just want to introduce that idea right now, and whenever I'll try to model that as often as I can in the front of the room. Okay. This this raises to mind, this, like I said, even as we were doing this, this brings back to mind this model down here. P of t equals P0 times 1 plus r to the t. Oh, something to memorize. No, not something to memorize. That's why I gave it to you after we did the problem, to prove that you don't actually need this, do you? Right? Like, this is still just y equals a times b to the x, isn't it? It's still that model. It's just b, or whatever you want to call that. Our growth factor is a little more complicated now. It's like 1 plus r instead. But still, 1 plus r together, 1 plus r is our growth factor. It's just like on the last problem, it was 3, or 3 to the 1/5, however you want to think about it. Same thing here, right? It's just, we're thinking about it in terms of percent growth rate. By the way, what would the model 2 to the t, what's the growth rate on that? Every time t increases by 1, what's the percentage rate growth? Careful. If this is 2% growth, then what is this percent growth up here? It's 100% growth, actually. Every time t increases by 1, y, or whatever we're doing, increases by 100%, right? Which is another way of saying doubles. All right, whatever. Don't worry about that too much. But I just want to make sure you understand what we're doing here. Okay. So this should be a review, but please, please, please don't memorize this as a separate formula. In fact, don't memorize it at all. Okay? That's the word I have for you about that. It looks like, oh, fancy. It's got a P sub 0 in it. Like, neat. Okay. Let's do another population problem. Where's my other excited reader out there? Someone. I saw a couple of them.
Where's the best? You said the best was B.
Who wanted it? No, for real. Lisa, go.
Okay.
Number 3.
The population of Rockville in the year 2000 was 47,380. The population was 57,402 in 2005. Assuming its growth is exponential, at what rate is Rockville's population increasing? In what year will the population be 500,000?
Excellent. Okay. I did look it up on census.gov, and that's where these are from. I need some new data, though, because we probably have 2010 or 2015 data we could pull, maybe. I don't know. That would be exciting. All right, but at the time, we can see how accurate our model is. That would be fun. Okay, so assuming exponential model, tell me what your thoughts are on this one here, if you haven't already started doing it. What do we do? Someone help. Okay, yeah, okay, that's fine. Yeah, what are we going to let? Let's let population be P be population after T, or T years after 2000. Is that okay? Okay, so can someone help me? What next? Yeah.
Well, from 2000 to 2005, there's a 21.13% change in population.
Oh yeah, yeah. Okay. Actually, I love what you're doing. This is not the way that I think most people are going to think about it, and I'm going to go with it over here. So, what does that mean?
So that means in 5 years, the population increased by 21%.
So, you want to write a model though for me?
So, for 47,388 times
1 point something.
1.21.
How about I just write this? Because I don't really feel like actually saying what you just said. Is that fair?
Yeah. But
To the
you have to oh wait, no.
no, actually, because that's just the growth factor, right?
Yeah.
To the T over 5, and so she's kind of taking a play out of our Instagram book from problem 1, isn't she? Like this kind of feels like, hey, over a 5-year period, we multiplied by this number, which I don't know what it is. It's 1 point something terrible. It's not nice, like 3, but we did. It's 1.2 something, she said. Okay, so that does it. In fact, we just wrote down the model. Boom. I like it. There is another way that my last class preferred when we first started this problem. Someone suggested something else, so I'll just say what it is. But I kind of love what we're just doing now. Actually, is what I kind of like this better. But what was your first inclination? Does anyone else have another idea? You could like maybe
Yeah, I just said it was 47 thirds. 388 times e to the x, and then plugged in 57,402, that's 5.
Yeah, so you could be like, well, I know that this has to be true. That right? And does that make sense? And you could solve, maybe some of you would have done that first, I don't know. And then you could actually solve for r. Yeah? Okay. So yeah, when you solve for r, we'll tell you what you should get. You're welcome to do that too. I don't know, whatever you want to do. So what is this? 57402 divided by 47388 to the 1/5. So another way to write our population model, I'm ready to actually maybe write this down here. Is 1.0391, whatever, to the t. So what is r? I mean, you could solve for it over here. Someone do that. Did you do this, Judah? Okay. You should get the same thing we get over here. Did you get 3.91%?
Yeah.
3.9,
3.9, but I lost some accuracy when I transferred.
Yeah, and by the way, if you did this and you want to store r in your calculator, do you know how to do that? If you obtain the value of r like Judah and I just did, somehow, you got r, you solved this, you took a fifth root, you subtracted one, whatever, you got r. If you want to use that in its full precision, and you never want to like later use 3.91% somewhere, okay? Then you hit store, and then choose your favorite letter. How about R? Alpha, whatever your favorite letter is. And now, anytime you use the letter R, it's this number, okay? So I would really suggest that. And it's more important than ever before. You hit store, and then alpha, whatever letter you like. It's more important than ever before because errors here literally get exponentially compounded. Your errors will literally get exponentially compounded as you go further out in your model. That error will just get worse and worse and worse, like really bad. Okay, promise. All right, how are we doing on answering the question? What is the rate that it's growing per year? It's 3.91% per year, or 23% is what you said per 5 year. 21% over 5 years, which is equivalent to 3.91% in a given year. That's what you'll get over here if you use this method too. All right, cool. And then we want to calculate when will the population be 500,000. So that's not interesting to me. I mean, it's similar to the problem we did before, but we are maybe curious about when Rockville will reach 500,000 people. That's kind of exciting. So let's figure out what that would be. And keep in mind that when I solve this, I'm going to be using the full value of r here, right, that I stored on my calculator. Okay? So solve that using techniques like you did in the warm-up or like you did here or whatever. So what do we get? What do I need to do? Log of 47. 388. Oops. I'm just trying to solve this all on my calculator here. Does that work? And then minus 1? Oh no. Divided by log of 1 plus r. Yeah, that'll do it. Geez, 61 years, people who tried it? Okay. So t equals 61.
It's not exactly
0.4532, etc. All right, but then it says in what year? So what year would that be? It's nice. The model we've created is nice. It'd be in the year 2061, which I think Lord willing, I think that we'll maybe all be around then. So we can actually check in a couple years. In 2061, we'll call you guys up and we'll talk. See if okay. I'm kind of actually doubtful about that. Actually, I think that this maybe highlight some of the limitations of an exponential model. Actually, I'm like, but maybe we're wrong. Maybe we will be a booming city in that time. Okay. And actually, we could just for fun.
Will you still be in this classroom?
I don't think so. We'll see. I'm hoping I'll be retired by then. We'll see. It'll probably be in about May. It'll probably be about May of 2061. In case you want to expect my phone call at a certain time. Okay. May of 2000. All right. We'll go with it. All right.
Put it on your calendar.
Put it on your calendar. Huh? All right. Let's move on. Before we read the next example, if you guys would stay with me here, I want you to take a look at some formulas that will harken back to Algebra 2 for you. All of these are titled up at the top, financial applications. Okay, the first one is no surprise at all. Remember that the first one is still just y equals a times b to the x. Just masquerading as something financial now, but it's still just y equals a times b to the x. The second one is actually the same thing too, but let me just refresh your memory about what this second model is used for and what it means. Okay, so a bank will advertise, like in the next problem, you'll get 3% quarterly or something, 3% interest annually. And that should actually say this on this next problem. 3% APR is what it should say. Or nominal APR, that's what it says, which stands for annual percentage rate. Okay, so if they advertise 3% annually, what they really mean is probably, like say they actually give you interest monthly, which is actually realistic. I don't know, do you guys have banks? Have you noticed when your interest payments come in? I don't know. I think I get an interest payment monthly is what I get. And if you have a bank account, you also know that your interest payment is like 2 cents or in a given month or something. Because interest rates are nowhere near 3% right now. You get a bank account, you open one today, your savings account will have an interest rate of like 0.1% or something. It's pretty terrible. So say it's monthly that you actually get payments. So what they mean is not, apparently, what they mean is not 3% at the end of the year. They pay you once, they calculate your interest, and they give you one check. Here's your interest from the year. They actually give it to you monthly. So what are they doing instead? Well, they're lying to you a little bit. That's kind of a good lie, actually. What they're doing is they're giving you a 1/12 of that. 3% divided by 12. But they're doing it 12 times as often. Do you feel that? Instead of giving 3% once at the end of the year, they give you a 1/12 of that maybe. Or here, quarterly, what would that be? 1/4 of that, 0.75% interest. They're not giving you very much interest, but they're doing it 4 times, right? Makes sense. What they're doing. Why does that make sense then that in this second formula we have a divided by k? Is that what we just said? If it's quarterly, we're dividing by 4. Or if it's monthly, we're dividing by 12. And then up in the exponent, that's okay. You know, that you're like, that's cool, okay, fine. But on the exponent, you get to multiply by that number too, don't you? Because if you're going to do it 4 times as often, then that makes sense that up in the exponent, you're going to multiply by 4 as well. So, I don't know. I think you've thought through this stuff before maybe, but I just want to refresh your memory about like why that formula looks the way it does. Because in the end, it's actually still just y equals a times b to the x. It's just b is suddenly like terrible looking. B is like this nasty, nasty thing. Now, okay, so I think that conversation's a good conversation to have. Well, yeah, so let's do this problem, then we'll talk about the last one there too. What's going on with continuously. Where else is my reader out there? Anyone? Beth, you want to read this one? Did you want to read number 4?
Oh yeah, sure.
Okay, go. And then will you lay off him? he's doing a good job. All right.
Somehow in the current economy, you find a savings account that yields 3% on the housing quarter. If her initial investment is $500, find the value of her investment after.
Okay, and this is of course assuming that she doesn't put anything in or take anything out for those 10 years. Okay. But that's okay. I mean, we can count. That's actually a good question. How would we adjust this model if you like were putting money in regularly? It's called an annuity, and it's actually not too bad to do. We just don't cover it in this section in this course, but you could do it. It's not hard. Okay. So, I mean, what I don't. This doesn't interest me a ton, but someone want to just say what the formula is? Write it all the way down.
500.
Justin's gonna take it. Go ahead.
Okay, 500, and then the parentheses name 1 plus 0.03 over 12 to the 12.
To the over.
Oh, we're doing quarterly.
Yeah.
To the 14.
There you go. Good. And then plug in 10. Well, that was just an example. You're right. But no, in the problem it says quarterly, so we'll go with that. And it should have said 3% APR in the problem. I apologize. That wasn't very clear, actually. So if you plug in 10, you get something, right? I don't know. Something. 674 and 17 cents. All right, we don't want to forget the cents. That's good. I'm just trusting Rachel that she's right. I don't know. Do you guys get anything on that? The same thing? Okay. All right, and then we want to say something about this third formula briefly before we go to the next example. The last formula up here is what happens, this idea of continuous compounding, is what happens in the second formula when you let k, the number of times you compound in a year, grow large, okay? So if we were compounding every minute, right, what would k be? If we're compounding every minute, come on. What would k be? Every minute.
A lot. Oh, it's that song.
Thank you.
525,600.
Well, that's
You don't
actually
know
not
that song?
true because
You don't know that song? Right. All right. The point is it'd be big, okay. Or if you did it, what if you compounded every second? If the bank was like, that'd be awesome if the bank was like, here's some money, here's some more money, here's some more money. It's not much, but here it is, here's more. So,
it's like Bill Gates.
yeah, that'd be like Bill Gates. Every second someone's like, here's some more money, here's some more money. It'd get bothersome actually, probably. All right, so as k grows really, really large, as in mathematical terms you might say, as k approaches infinity, the second formula becomes indistinguishable from the third formula. Okay, and e here is not a variable; it's a constant. It's the one we're familiar with. It's the base of the natural logarithm. Yes, Euler's number 2.71828, etc. All right, listen. Please, stay with me. That was good. I like that. E, and maybe when someone introduced e to you, they actually gave you the definition. I don't know. One definition of e though is the following expression, right? All right, so this makes sense because this is like what we're doing here, these two formulas, okay? This second formula, like I said, just approaches this third formula. Here's a really, really simple case. Say I give you, amazingly, I offer you 100% interest.
Oh my God.
All right? I offer you 100% interest, and you're going to invest $1 for 1 year. The amount of money you get at the end of the year, if you compound continuously, is $2.72, approximately.
How'd you know that?
Because that's E. You have E dollars at the end of the year. So, in fact, this is an important definition of E. We'll give you another definition of E later in the year too, which is equally interesting and beautiful. It's so interesting and beautiful that it's painted on the math hallway over there somewhere down the hall.
Oh, that's not pi?
There's no. This expression. It's over down. I don't remember where. Somewhere down the hall. Over Miss Engelman's room or something. I don't know. All right. I need to hear from Peter. Go, Peter.
When you compound continuously, shouldn't it be infinite?
Turns out no, because you're getting infinitely less. So it's kind of like a little bit of a race, right? We're giving you not very much money, but we're giving it to you really often, right? And that becomes more and more true. So it's kind of like a race. Which one kind of which one evens out, right? Over time. We're giving you like basically nothing. In the infinite case, we're giving you interest all the time, but it's basically nothing. Does that make sense? So they kind of battle it out a little bit. All right. And by the way, you can find a value for E on your calculator by actually typing in parentheses 1 plus 1 over a million to the million power. And you'll get approximately E on your calculator, right? That's what this says. All right, can we say something briefly, at least please, about number 5? I guess we won't have time for 6, but that's okay. We'll do number 5 at least. It says, I'll read it because just for the sake of time. Mr. Chi has $1,000. What annual interest rate compounded continually is required to double his money in 15 years? So compounded continually or continuously is a highlight there that we want to make sure we say. So how much money does he want? He wants $2,000. He has 1,000. He's compounding continuously, so we're going to use that third formula. E to the R, and T we know is 15. R we don't know. Okay, so we could solve for R. If you do that, you'll get 1/15 ln2, which is 4.62%. All right, so that's the interest rates he needs. But let me ask you this before you go. Did we need to tell you this? Or could we have just asked, what annual interest rate compounded continually is required to double your money in 15 years? No. We actually didn't need to know that. If you start with $1, how long would it take you, or excuse me, what percentage rate would you need to double your money? 4.62%. It doesn't matter what you started with, actually. The second step in this equation will always be.
So you could have made it a lot easier by just using 1.
Yeah, exactly. I mean, the very next thing you're going to do when you're solving this equation is divide by 1,000, no matter what, right? So. All right, homework 4 tonight.